about focus on anywhere, anytime you can rapidly produce something. So it's relevant to current quite hot topics about 3D printing, but it's a bit extended from current technology. So this probably some of you are familiar with them. One is the FDM, that's a very popular one, low cost. Almost everybody can afford it. The second one, this one is the LA, is a little bit more expensive in terms of machine. It's UV cross-linking. It's a different ways with particles. This one, the third one is DLP, is a kind of UV cross-linking. It's pretty faster, but it's using later I'm going to mention more about it. It's using this kind of liquid material. And the last one is PolyJet. This is quite fantastic. Last 2 weeks ago, I visited a workshop. There's a workshop about current PolyJet technology, 8500. That is really fantastic. It's real color, multiple materials. It's probably the up-to-date technology from Stratasys. But anyway, I'm going to discuss a bit different from that. I'm going to address two special scenarios, for example. That is, first is microgravity. The second is strong random vibration. The first is in the space station. How are you going to print something over there, because it's a microgravity environment? And so this is a couple of years ago, pretty slow, and basically similar to FDM. And the FDM technology was firstly applied by NASA in space some years ago. Of course, this is, as the video itself, you can see it's pretty slow. So can't print something, manufacture something in minutes. Instead, it takes hours, sometimes it's days. The next scenario is like this. Random and strong vibration, otherwise like this. So can you imagine that if you want to do something, I mean, when you leave home, you drive a car to the office, and on the way you can print out something instantly within minutes. That will be more interesting to see, right? So that's what we are working on. We want to first rapid manufacturing, and then the okay. So sorry, what's wrong? That's only. So, well, so sorry for the problems. Seems this is the only way. Anyway, if the screen is sharing, well, I can use this one. Okay, let's continue. And so the problem we try to solve is that we try to develop technology so that we can instantly work out something, actually fabricate something, anywhere, anytime. So let's take a look of those so-called rapid additive manufacturing technologies currently available. The first one, some of you may be familiar with this, these pair of shoes from Adidas. They use this current technology for the continuous liquid interface production, DLP actually. So it's able to print something, to come out with something rapidly in minutes, or half an hour, something like that. Or the most recent one that's called the volumetric additive manufacturing, in which two beams cross-link a point. And this kind of technology is rather a lot faster, even compared with DLP. It was reported that it's able to print something like human ear size in minutes, in a few minutes. So, but you can see all of them using liquid, so that you will definitely have a problem to print in the scenarios I mentioned in the previous slides. So let's go back to the traditional way, solid processing technology, solid state processing technology. Yeah, laser engraving. This basically is able to produce micro cracks inside of a crystal. Of course, this is not this kind of technology, so we use it for 3D printing. So, that inspires us actually from very beginning. Can we lay UV crosslink a solid piece of material, So definitely it should be solid, and also it should be transparent, so that we can use UV to crosslink inside of this transparent solid material. So we start from here. It's called solid state photo crosslinking, where that's possible. So let's take a look at a very special type of hydrogel, a special type of thermal gel. This material is unique in the sense that it becomes liquid upon cooling. So it's melting upon cooling instead of melting upon heating, as we learned from the early days. So let's demonstrate the process. How we're going to do that is that we have the solid state of this particular thermal gel, solid at room temperature, and we place a mask on top of it, and then use UV to crosslink. After UV crosslinking, we come out with this part crosslink, and the rest are not. Because as shown in this video, it melts upon cooling, so that we can cool it. For example, place inside our fridge, and then the rest is crosslink part. So this is the concept. So how are we going to achieve that? Okay, we have we're going to demonstrate the concept. We are still working on that by the end of this in the very last slide. We are working on that, and we have actually achieved a little bit more, but sorry, I have to keep it secret at the time being. We will start with a transparent container and then put the liquid material inside of it at room temperature. At room temperature, it becomes solid, okay? Because it's a very special type of hydrogel. And we place the mask on top, and then UV crosslink from top. And then we turn that by 90 degrees because it's not liquid, it's solid. So then we can turn that by 90 degrees and then mask on, UV crosslink again. And after that, we come out with solid piece, and then we can cool it to wash away. For example, we can use the ice water to wash away the uncrossing part, and then we have the shape we want. So there are a few things we need to consider. The first is whether the material is strong enough. I said it is solid, whether it's strong enough. We place a pile of coins on top. Yes, it is quite strong. And this is after cross-linking. After cross-linking, you can see it's still solid. And then, sorry, And then this is after cross-linking one piece of sample. You can see, it's quite viscoelastic. And sorry. And lastly here, this is a video to demonstrate the whole procedure. We take the material out of the fridge, so it's a liquid, and a while later it becomes solid because it heat up to the room temperature. And then mask on, UV crosslink. And then we can turn that by 90 degrees and UV crosslink again with some mask in between. Now it's time. We use ice water to wash away the uncrosslink part. And here this is the remaining. Yes, it's a cross as we expected. Okay, we achieved this a couple of years ago. And of course, there are lots of limitations because this is first, for example, this is hydrogel, so it's quite soft. Now, let's take a look of the mechanical response of this thermal gel. This is a stress versus strain relationship of this material in compression, cyclic loading. And because it's viscoelastic, so you can see it doesn't actually fully recover its original shape. But this actually is the nature of the visco material. A while later, it's able to recover fully. And now this picture is about the shear memory effect. You may wonder that what is shear memory effect and why do we need the shear memory effect? Originally, this is same cross-section cylindrical shape of the material, but if you leave in air for overnight, you will see the top part shrink significantly. The reason is that because of water evaporation. That's not bad actually. It's very good for us to show that it doesn't directly relevant to the amount of water content. So we can place inside of the fridge to soften it because it becomes liquid. Certain part of it, and then compress it and take it out. So this becomes the permanent shape. This is called programming. Obviously, most of the material, we heat up the material, soften it, and then program into the temporary shape. But for this material, actually, we cool it, soften it, and then we fix the temporary shape. This shape at room temperature is going to be there kind of forever. Of course, this hydrogel won't be able to last forever. And then you place this deformed shape back into the fridge. It's going to fully recover its original shape. Now, the question is that this is about the shear memory effect. The unique feature of this particular material is that cooling responsive instead of heating responsive. But you may wonder that why do we need the shear memory effect? Okay, let's explain why. Because in the previous step, when we try to separate the uncrosslink part from crosslink part, actually the material deformed significantly. If it doesn't have the shear memory effect, what might happen is that the shape won't be so precise, the result one. If it has the excellent shear memory effect, it's all to recover back to the original shape as we wanted. We have a video here to demonstrate its shear memory performance. And the original shape we should expect to be the ice shape. Now we cool it, but it's not cold enough, the water, and therefore it's recovered but not fully. So this is cooling responsive shear memory effect. And the second one, we place the deformed shape on top of dry ice. So now it's cooled to much lower temperatures compared to the previous part. The material is a little bit sticky, so we help a little bit to get more recovery. Okay, now we have two materials with different composition, and we can see that in terms of recovery, for both of them, are able to fully recover them or recover their original shape in 1 hour. But for one material is able to, this one, within 10 minutes, it's almost fully recovered its original shape, but the other recovers less. Okay, the next. This is quite complicated. And the material we previously mentioned has the water content dependent heating, cooling, water response shape manufacture. But I don't want to touch too much about it. If anybody interested in that, you can scan this QR code and then for this reference recently. So this is about hydrogel. Of course, it's soft, and therefore, practically, how are we going to implement it? We are going to use dual beam cross-linking, similar to the current volumetric additive manufacturing. But over there, they use liquid material for cross-linking, but we can now use solid material. So here we go. This is animation. We basically need two beams, two UV beams. One is flat, one is kind of point. So a combination of these two is going to cross-link a certain part. So after that, we can wash away the uncrossing part. So this is supposed to be the remaining part. My understanding is that the volumetric manufacturing technology is going to be available in the format of open source. So I expect that they can come out with the machine, because the machine itself is definitely not my expertise. So I hope that very soon they're going to come out with the machine, so we can use all the material over there to demonstrate the solid state cross-linking and the rapid manufacturing. So of course, the previous one is a soft hydrogel, actually too soft. There might be some applications in biomedical engineering, but in terms of normal mechanical engineering, we do need hard polymers instead of very soft ones. Now, we need to introduce the concept that is between thermoset and thermoelastic. I'm not sure how many of you are familiar with these two terms. The difference between thermoset and thermoplastic is cross-linking. One is if you heat up, it's going to melt and flow, that's thermoplastic. The other is that if you heat up even high temperature, you can burn that, it still keeps the shape. So that is thermoset. However, there's one particular type of material. This term, which was invented about slightly more than 10 years ago. That's called Virtual. And the particular feature of Vichman is that it has a reversible cross-linking. So the cross-link is not permanent, as in thermoset. And this illustrates the cross-linking against the temperature relationship for this material. So upon heating, it's fully cross-linked 100%. Upon heating, over here, cross-link starts to disappear gradually. So eventually like this at a high temperature. So it becomes thermoplastic. But at low temperature is thermoset. And upon cooling, the cross-linking is going to fully recover and therefore become thermoset again upon cooling. So this is the feature of bitumen. And then let's give a little bit introduction about one particular commercially available bitumen, that's TPU, thermoplastic polyurethane. This term was actually from the manufacturer. This is brand name 262A. And if you do carry out a differential scanning measure test in 2 cycles, you will find the heat flow against the temperature relationship. Over here, this trough indicates melting. And therefore, we expect that the material become fully melt at about 75 degrees. So this is a dynamic mechanical analyzer, DMA, against the strain relationship. We keep the strain almost constant, and we apply a cyclical loading. So within temperature about 40 to 50 degrees, you will see the response. The strain response is rather periodical. So which indicates the material is quite elastic. And if you heat up 90 degrees, which is well above its melting temperature, as indicated over here, 90 degrees, the material is still able to maintain the shape. As you can see, the strain is still about constant. Although it's not so periodical as within this range. And even you heat up to 100 degree, the material is still able to maintain the shape. The strain not so periodical in response to periodical load, but it still maintain the shape mostly, unless you heat up to over here. Then you will see the material lost the shape, so it becomes thermoplastic. Okay, easy to flow. So this is a particular feature of bitumen. We can cross-link the bitumen. Of course, it's not particularly designed, the bitumen, particularly for the application we're going to use. Later, I'm going to mention about something else, some other material which we have developed. We need to make sure that the material is transparent. So we heat this part of this bitumen, we can see it changes from translucent to transparent. So of course, this is very good for UV cross-linking to the dip into the material. And the second, as I previously mentioned, is about after cross-linking, whether the material has a shear memory fat. Yes, the material has a very good heating responsive and chemical responsive shear memory fat. This heating responsive, which means that upon heating, it's able to fully recover its own shape. And chemical responsive, for this particular material, we use acetone. Of course, this is not an eco-friendly method for shape recovery. We simply use this to demonstrate that it has excellent shear memory fat. So yes, the material has excellent shear memory effect to ensure accuracy of the produced item. And in terms of stress versus strain relationship, this is a tensile stress versus tensile strain relationship. Cyclic loading for two types of materials. And you can see the modulus is 130 megapascal. This is a lot stronger. Bear in mind, bitumen is a type of material, just like thermoset or thermoplastic. It's not one particular material. So we can tailor the mechanical properties of bitumen in many ways. I'm not in that field, so I leave to my colleagues to come out with a version of this. Room temperature UV cross-linkable bitumen. And she developed this is the formula for this material, for this particular bitumen. And the bitumen has excellent shear memory fat, so which means that upon heating is able to recover its ultra shape. I have mentioned about the importance of having this shear memory fat in this solid state cross-linking. Here we have a video to demonstrate this room temperature UV cross-linkable material. We dissolve the solid material in chloroform. Of course, we can heat up to melt it, and then spread on top of a container to get a film shape. So after evaporation of chloroform, now we have a piece of transparent film. Next, we replace a mask, aluminum foil on top, and then UV cross-link it. After that, we heat up, so we can easily separate just using hands to separate the uncross-link part from the cross-link part. And because of shear memory fat, we can always ensure that the shape we want is always there. Okay, so this is room temperature UV cross-linkable material, in solid state. And now we come out with actually recently, not exactly very recently, 2 years ago, we found a particular type of resin which is commercially available, which means that low cost. The cost of this material in terms of per kilogram is about same as the filament used in FDM, for example, PLA used for FDM. That's about around 20 Singapore dollars per kg. And this particular type of resin commercially available is about 20 Singapore dollar per kg as well. So, which means that easily we can apply this material for mass fabrication instead of the previous room temperature cross-linkable material. My collaborator, she can only manage to produce 5 to 10 grams per day, 5 or 10 grams per day. But now we have a supplier low cost, and also he can produce this kind of material a couple of times per month. So you can see that's the reason we love this love that. Okay, so here we have the first video to demonstrate utilize this particular type of reason, solid state cross-linking. Now it's solid state, so we can use hand to manipulate that. And under unstable environment, we shake it deliberately. And UV cross-linking after that. Now we can find the piece we want. The shape is very much depends on the mask we use. It's supposed to be a musical note. Okay, this is one way to separate the cross-link part from uncross-link part. And the remaining material, which is uncross-link, we can reuse it, as you can see. And we do the same thing, and shake again, using cross-linking. And this time, we're going to use boiling water, hot water, to separate the cross-link part from uncross-link part. Yeah, okay, we use hot water for separation. It appears that using your hand to separate is more effective than using hot water. Okay, because of the uncross-link part upon heating to high temperature is quite sticky. Okay, this basically demonstrated, this video demonstrated the possibility using the commercially available resin. And here we use the same resin, but this time we demonstrate the possibility to use two beams to cross-link a particular dot inside of this material. Now we have a piece of material. We're actually using hands to compress it into this cube shape. And now we have two UV to cross-link, actually join together from one particular point. That particular point is going to be cross-link. Yes, we're just still struggling to find that point. Yeah, finally, here we go. We have a small dot. Yes, that's what we want. And this video demonstrated the possibility to use two beams to cross-link one particular point. And the remaining material, we can use our hand to reshape it into cube shape and reuse it. This is another very, very important point because for manufacturing point of view, cost effective, you definitely have to consider how much material you can reuse the remaining material. So in this way, we can effectively reuse all the material. Okay, so that's basically is what I want to talk. And more recently, we have modified a laser engraving machine with the UV head for cross-linking. And probably next time I'm going to discuss about that. So summary. We have come out with a technology, an idea actually, at this stage, so that we can apply this technology for rapid 3D printing, rapid manufacturing, on space, air, and sea missions, so we can achieve rapid manufacturing anywhere, anytime. Now we have the material, although we don't. Eventually, we found that at this stage, we found that we can use commercial material to achieve that, which means that low cost and the technology is ready to explore very kind of applications. So thank you very much.